In our previous video on functions, we stopped on this slide, so we'll pick up from here. So I said when we saw how to create a function in C that the function needed a return type as well as to know the types of the values being placed or passed to it. However, there's times when your function doesn't return something, and there's times when your function doesn't receive anything. So we still need to put something there, and that something is the keyword void. So this function receives two ints that will be known as number one, number two down here. It prints their sum, but then it doesn't return anything. So the return type is void. And likewise, we could not pass anything to a function, and we would use void in the parentheses here. And in fact, main is a function, and since we're not passing anything to it, the type for what we call the parameters is void. So that leads me into something of a philosophical discussion. You'll notice that when I've been writing my code in previous lectures, I'd write something like this: int main void. So we do this. Okay, let's do this. Int a equals 23. Technically, I don't need standard I/O because I'm not printing anything. And that program ran. We didn't see anything because we didn't tell it to print anything, but it did technically work. So what's the issue? Well, since this is a function, when I write int here, technically I'm claiming that main returns something. So, strictly speaking, if I'm going to write int there, I should return an int. And when your program ends successfully, like it did in this case, I assume, return 0 is typically what's used. So if we try to compile it again, we get this to prove that it really is doing something. Something like that. And notice it didn't affect the program running. So what's the purpose of this? Well, it is possible at more the operating system level to pass numbers that then are received and then something is done based upon the value returned. So if you're using, like I am, the bash shell, BASH, on Linux, and they also exist on Mac, when I run my program, then I could say echo space $? And get the return code from this. So that was 0, that was 0. You might think, well, that's a coincidence, right? Let's put 123 in there, recompile the code, run the code. There's my 123. So I personally tend to leave it out because I'm just lazy. And I personally don't think that I'm doing anything in which it's going to hurt anything. Now, would there be times when I would think that would be appropriate to make sure I return something? Sure. But I don't think for most of the C programs I write that it matters. Now, in the C89 standard, which I'm teaching, not using the return there technically leads to undefined behavior, meaning I don't know what's going to happen. In fact, let's run it and see what happens. 7. 1, 2, 3, 4, 5, 6, and technically a new line. So it could be I'm getting 7 because that's what printed, and technically printf does return something, which I'm not catching. Let's see if we can mess things up. Oh, I need to recompile. Still get the 7. So I think it's probably picking up the 7 from that, but I can't say I know that with certainty. Now in the C99 standard, if you don't put a return statement here, the compiler will insert return 0 for you in terms of what it does, which also supports my idea that it's probably not that big a deal in most cases. But strictly speaking, if I'm going to say int here, I should have return and give it an integer. Okay? But I probably won't. So we saw in my example that had a function I wrote that I put the function definition at the top. But it's actually much more common to do something like this. So let's say I have a function. Say it returns an int. So int f, int x, for example, return 3 times x plus 14, and that's going to be an int as well. Oops, semicolon. Right, so I compile this, run it. 44. 3 times 10 is 30, plus 14 is 44. That worked fine. I can do that. But it's probably much more common to do this. Put the definitions for all functions below main. Main is the function that will execute first, and then other things build upon that, or will be started from that. So here's where I put the function definitions, which once again are the descriptions of how the function works. Of course, the programming logic indicating that. But when I do, then I need a function declaration up above main. And in fact, that's what include standard I/O is doing for printf or the other functions. Right. So what do those look like? You can do them in slightly different ways in terms of whether or not you include the variable names. But in order to avoid mistyping things, I prefer to just simply take what I have here, cut and paste it, bring it up to here, and now change that curly bracket to a semicolon. The space there doesn't matter. And we get that right there. So this is my preferred way. So if I have a whole bunch of functions, I put them down here and then I put the function declarations here. So why do we even need to worry about that? Well, there's a couple reasons. One is it's very common to have, if you write a lot of functions, to put those functions in their own library and then simply import the library like I did here. But just as was the case if I leave pound include standard I/O out and then I try to call printf here, the compiler is going to complain when I move these functions to another location and then try to use the function. I can have a problem. One of the things the compiler is trying to do is help me out by looking at it and saying, for example, that, well, you said that you're going to give me an int and you're going to return an int. So right here I'm giving an int and it returns a value. It looks like I'm using it correctly. If instead I accidentally did this and try to compile it, now it's giving me a bunch of errors because this right here doesn't match with this or this. Even if I come down, I take this right here and add that in. So now the definition and the declaration match. I still have a compilation error because it says too few arguments to function f. Well, it says you're giving it an int and a double, but I only give it an int, so that's why it's too few. So it's there to help me, especially if the function definition is somewhere else, because it is possible to compile the file without knowing what the definitions are yet. So the declarations are there to help us. Another potential problem, and sometimes compilers will help you out on this too, but they don't always, is what if this function in turn called another function that was defined later? Well, you still can run the problem that by the time this function is called and then attempts to say if I'm doing this, g, call that function g, but g is defined down here, well, you're still going to have a problem where it doesn't know what g is at compile time. So having all the declarations up here helps that out. And you don't have to worry about make sure you have the right order, because if you have the declarations up here, g can come before f, or f can come before g. It won't matter because they'll all be seen by the time you get to this. But if you're putting the functions definitions up at the top then sometimes you can have a problem if the order is not the same as we're calling things. So this is probably the much more common way of doing it, to put declarations at the top, definitions at the bottom. So here I'm doing what I just talked about. Notice here I leave out the variable. That won't hurt anything because it still says you expect to receive an int. And in fact, even if I put in a variable name up here, they don't even have to match. I could say int zebra, and it still would work because it really cares about the int and the void matching, not the variable name. We've seen this a number of times now. Virtually every program we've written has had pound include standard IO. What if I do want to create my own libraries? Well, the syntax is very similar, except now I'll use the double quotes. And in this case, this would assume that my functions.h was in the same directory as the function calling whatever function is stored in this file. If you're going to use a different location, then you need to have some way of indicating the directory change, either an absolute reference or a relative reference. So our last topic, which is very important, is the idea of scope. So for the functions that I've written so far, we say that the values that I've passed have been passed by value. And when you do that, technically you make a copy of things. But the variables that I declare within a function block are local to that function. They're unknown to other things. So let's see how that works. So let's say we do this. I want to write something that doesn't work correctly. So let's say I do this. We say, okay, int y equals 30. And I come down here and say y. So I'm passing in 10, which gets the value of x. And this says return 3 times x, which should be 3 times 10, plus the 30 that's right here, all to be assigned to A. Error, y, undeclared, first using this function. This y is unknown to this function. It was declared locally, so it's only known within this function, or technically even only known within this block. All right? So if I want y to be known down here, I have to pass it in if it's declared locally like it is here. So if I did this, and then give it y, and let's make it something other than 30. Let's make it 40. Compiles fine. And so 3 times 10 is 30 plus 40 is 70. So that works. These variables, how does this work? Essentially, down here, these lines right here, for all intents and purposes, are doing this. Now, this would be illegal to try to redefine these variables. But it's as if when I do the function call here, I wrote int x equals 10 and int y is equal to 40. Okay, that's what's actually happening. Now this would be illegal. We can see that. Oops, sorry, I need to save this over here. Error X redeclared. See, I can only do it once. I can't redeclare, even up top. I can't come along here and say int y equals 50 now. That's illegal. Right? So we saw it there. So I can't declare a variable more than once within the same block. And these names don't even have to match. This y is different than this y. So let's say I do this. Y is 40. So let me not pass anything to this function just to make it more clear. So I'm going to simplify this sum to make it easier to focus on what we're doing. So I'm not passing anything, I'm not getting anything back. So void f void. Take that, put it down here. Change this to this. Right. Line these up. Let's see it again. So what happened? We create a variable y of type int, give it a value of 40. Then we call this function. Inside this function, we create a variable y called 99. But the memory location of this y is different than the memory location of this y. They're two different variables. So I could have called this something else. These are no more the same thing than it would be if I said int y here and int z here. They're just two different things. So here I print the value of y, which was 99. Then I increment y by 1, print it again to get 100 to show I can change this y, reach the bottom of the function, so I automatically return to where I left off, which is right here. Now I print y, but now we're talking about this y, which still has a value of 40. So changes here don't affect changes here for the way these are created. That's called variable scope, is the idea. There is an idea of global scope where we could define values outside functions that are then known globally. But those should be used under the appropriate circumstances and certainly aren't intended to not learn how to use functions correctly. So don't think that you have to make variables match. Also, if we did this, so here's y. If I say this is int a, call that a, and this doesn't even have to match, call that int b. Worked fine. Printed this y, or excuse me, it hit F first, because what was passed was not y, but the value stored in y, which is a 40. So the way logic works is int a equals 40. It printed the 40, although down here it's stored in a variable called a, which is still different than this y. Even if this was called y, it wouldn't be this y. And once again, this right here is simply there to help the compiler. I could do this, and it's still going to work. It just needs to know you're passing an int and you don't return anything. That's what this is for. Okay? So in our next video, I'll write some more functions as applications. So we'll look at some problems and then see how to solve those problems using functions.